Okay, guys, let's get started. So I'm recording this video because we cannot have in-person lectures. Okay, so in the previous class, we learned that so we need to improve the performance of cache hierarchies, right? So and then how can we improve the performance of caches? So as you can see, this is the AMAT. This is the equation of the average memory access time. Is called AMAT. So as you can see, AMAT is composed of hit time plus the miss rate multiplied by miss penalty. So hit time is the common access time. Okay, so but the performance of a cache is determined by this this factor, right? So this is miss rate, these are miss rate and miss penalty. So actually the miss penalty is also determined by the characteristics of low level caches or the low level memory, right? So actually in the current cache, we need to reduce the miss rate, right? So so I briefly explained about the associativity of cache, right? So, and then I explained about the performance issues of direct mapped cache. So what was the performance issue? The performance issue is that, so in the direct mapped cache, the index. So actually using this index, we determine which block will be accessed in the cache, right? And then we use the part of address as the index field of the cache, right? And then so I just showed the very uh, a specific example, but so actually this example can explain the performance issues of a direct mapped cache, right? So there are two variables A and B, and then these variables will access the same cache block. So it is because so the addresses of these variables are different, obviously different, but the index field can be the same. That can be possible, right? So because the address is determined by tag plus index field and also the byte offsets. But so this is the very the rare case. But anyway, so these two variables can have the same index field here. So then what is the problem? So in the iterative loop, the A and B will be accessed repeatedly, but I explained that the A will be allocated first, and then B will be B will be requested. So in this case, the B is not found in the cache, so A will be evicted. Okay, then B will be allocated in the cache. Okay, but in this iterative loop, the A will access the cache again, but the A is not found. Why? Because the A was evicted already, right? So in this loop, so in this iterative loop, the this so allocation and eviction will be repeated, right? So this is the problem. So what is the problem? So in this example, we can observe temporal locality, right? Because this is the iterative loop, and then the same variables, the A and B, will be repeatedly requested, right? But problem is that A will be allocated and then evicted, and then B will be allocated and evicted. So before the data is used in the cache, this data will be evicted. Why? Because these variables are mapped to the same cache index, right? So this is the problem. Then how can we handle this problem? So how can we solve the performance issues by this direct mapped cache? So it's simple, right? So if the cache, so to the target cache index if the cache has multiple available slots, right? Available blocks, then A will be allocated, and then the B will be allocated in the available blocks, right? Then the A will not be evicted because, so in this cache, so with the same index, then this cache can include multiple blocks, right? Then A will be, so when the A is requested by this for iterative loop, then we can observe cache hit. B is okay, so because the B is not evicted when the A is requested, so when the B is requested, then we can observe cache hit in this case, right? So, so, so what is the characteristics of this cache? So what is changed with the for the same index of the cache? This cache can include multiple blocks, right? So this cache includes the multiple slots for cache block, right? So we can include some but the multiple blocks even though the index field is the same, right? So this cache is called the set associative cache. And then this property, so it means for the same set, the a single set can include multiple cache blocks. And then this property is called associativity of cache. Okay, and then this cache is called the set associative cache. Okay, so so we can we can find some different kinds of set associative cache. So for the maximum case, so maximum case is that maximum case is the fully associative cache. So it can be called the FA cache. So associative, fully associative cache. So fully associative cache means that the requested block can be allocated in the any available blocks in the cache. So in the fully associative cache, there is no concept of cache index. So what is the cache index? So this is the cache index, but using this cache index, we can just locate the this index, the address of a cache entry using this cache index, right? Right. This is just the index, but in the fully associative cache, the fully associative cache does not utilize indexes in the address field. So which means the cache block, when the cache block is requested, and then if this request is missed in the cache, this block can be allocated in the any entries, in the cache. Okay, then how can we identify the stored cache block? So we can use the tag, right? So in the fully associative cache, in the address field, there is no index field, right? So there is the byte offset because the cache block can include the multiple bytes data, but after the byte offset, there is a tag field in the address field. So using this tag, we can just identify the stored data. So which means the data can be stored in the any location. So any available entries in the cache. So this is the fully associative cache. So in order to access the data in the fully associative cache, then we need to check. We need to check all entries. So what does that mean? So we need to compare the tags in the all entries in a cache. all entries. So which means if there are 1024 entries in a cache, then we need to compare all 1024 tags in the cache with the tag field of the requested, the memory request. Okay, the tag field in the memory address. Okay, so it requires the many comparators. So we need to compare the tags, the many tags. So it's very expensive. Okay, it's a very expensive because it requires many comparators. So we can also consider some different type of a cache. Is called the set associative cache. And then when you mention a set associative cache, we can call it's the n-way set associative cache. So which means, so this cache has the set, okay? And then in a single set, this cache can include up to n blocks. So n cache blocks, okay? N cache blocks, okay? So what does that mean? So in the set, so index is determined, then the cache block can be allocated. And then for this target cache index, so we can store up to n cache blocks. Okay, and then this cache is called the n set n-way. Okay, n-way set associative cache. Okay, so n determines the how many blocks can be allocated in a single set. Okay, single set. Okay, so any set associative cache requires n comparators. So compared to this fully associative cache, the fully associative cache requires the the comparators as many as the number of cache blocks. Okay, but in a set any set associative cache, we require n comparators. So it's less expensive than fully associative cache. Okay, but the performance can be lower than the fully associative cache, right? Because so it's restricted. So in a single set can include up to n cache blocks. This is the n-way set associative cache. The performance of set NA set associative cache is higher than the direct mapped cache. So it is because in the direct mapped cache, in a single set, we can just store one block. Okay, but in a NA set associative cache, we can store n cache blocks. Okay, so we can avoid some uh some freak on we can avoid some data eviction, like this four iterate loop and A, B, and then A and B are mapped to the same index in the cache. Okay, so this is the NA set associative cache. Okay, so this is the example, and this example shows that so all caches include the 8 cache blocks, which means 8 cache entries. So in the direct mapped cache, the index field, the number of bits in the index field is log 2 and number of blocks. Okay, so this is the direct mapped cache, right? So in this case, number of block is 3. So no, number of block is 8. So the number of bits for the cache index is 3, right? So in the address field, then we just use the 3-bit of cache index field, and then each index, for each So this is also called the cache set. Okay, for one index. So for one index can only include the one cache block. Okay, so let's see the set associative cache. So you can find the set number. So instead of a block index number, so we use the set. And then in the set associative cache, in a single set, we can include multiple blocks. Okay, so you can find there are 4 sets. Okay, so in a set associative cache, the index field, the index field, the number of bits in the index field is determined by number of sets in a cache, right? So index field, number of bits in the index field is the log 2 and then number of sets. So how many sets in this cache? So you can find there are 4 sets. So the number of bits in the index field is 2. So using this field, we decide the set index, right? And then in a single set, so this is the two-way set associative cache, right? So what does that mean? In a single set, we can include the 2 cache blocks, right? 2 cache blocks. So we can just store the newly allocated data in the, 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 the one of 2 cache blocks in the target set. Okay. And then when the data is requested in the cache, then we firstly identify the set index using the 2 bits in the address field, and then we compare tags in the target set. Okay, so as you can see, we require 2 comparators because this is the two-way set associative cache. And the fully associative cache. So there is no index in the fully associative cache. So which means the newly allocated data can be allocated in any location, any blocks in a fully associative cache. So there are 8 blocks here. So and then if the new block is allocated, then new block can be allocated in the any empty blocks. So it means any invalid blocks in a fully associative cache. So the data is requested, then we need to compare all blocks. So in this example, there are 8 blocks here. So we require 8 comparators for the fully associative cache. Okay? Do you understand? Understand? So, uh, so this example shows the various set associativity of the cache. Okay? So it's a set associativity. So what does that mean? It's a direct method cache, right? So a single set includes the uh, sing, a, sing, a single one cache block, right? And then 2A, then you can, so if there are 8 entries, so 8 cache blocks, then in the 2A set associative cache, so each set can include 2 cache blocks like this, okay? And then, so which means there are 4 sets here. How about the 4-way set associative cache? In a single set, we can include the 4 cache blocks, right? And then if the n way, so if the set associativity of the cache is the same to the number of blocks, which means it's the fully associative cache, right? It's a fully associative, so there is no index field here, okay? And then the allocated data can be allocated to any entries in a cache, okay? So let's see some performance. So then the access patterns of the in the cache using this example. Okay. So let us assume that the cache includes 4 blocks. Okay. So there the so the cache can include the 4 blocks, and then we will compare the access patterns of direct mapped cache and then two-way set associative cache, and then fully associative cache. And then, so, this is the block address, right? And then this is the block access sequence, okay? So let's see the direct mapped cache. So because this cache includes the 4 cache blocks. So and then this is the block address, right? It's a block address. So then which means that we can ignore the byte offset, right? Right. So then how can we identify the index of these block access sequence? So we can just use the 2-bit, right? Because there are 4 blocks, and this is the direct mapped cache. So which means this cache has 4 sets, right? So we can just use the LSB 2 bits as the index of this cache. So because this is the block address, not the byte address, right? So as I mentioned, we ignore the byte offset because this is just the block address, right? So if you see the last 2 bits of these addresses, block addresses, so this is 00008, 00008, so 1000. What is 6? 6 is the 1, no, 1, so 4, 110, right? So the first address, the request is 0, then the cache index. So this is the last two bits, right? The cache index is 0, and then the firstly it's miss, right? Because the cache was empty. So all cache blocks are invalid. So it's a miss. How about the 8? Cache index is 0. So 8 will target the cache index 0. But the tag is mismatched, right? Because only the block address 0 is here. So what is the result? The result is miss because the tag is not mismatched. Tag is not matched. Okay, so it's a miss, and then because this request is missed in the cache, then we need to allocate the new cache block. Okay, so its address is 8, and then this is newly allocated in the cache, right? Then how about the next request? The next request is 0. What's the problem? Oh, it's the same cache index is target. Then, actually the memory 0 is already evicted, already evicted from the cache, right? So the memory 0. So actually this is miss because the tag was mismatched, right? So it's the miss because it was already evicted. So and then it's missed. So and then the memory 8 is it will be also evicted, right? Because we need to allocate the memory 0 in the target cache set, right? And then 6, so this is the target cache index is 2. So actually it's a miss because this is the new access for the address block address 6 and the 8. So what's the problem? The 8 was already evicted here. So it's miss. So what's the result? What is the result of this cache access? All misses. Okay. So there are 5 cache accesses, but all cache accesses are missed in the cache, in the direct mapped cache, right? So hit rate is 0. Hit rate is 0. So how about the two-way set associative cache? The 0 is the first access is missed, obviously. 8, so it's also missed because it's the first access. But what is different? So in a two-way set associative cache, there are two sets, right? There are two sets, okay? Because in this example, we have the cache includes the 4 blocks, and then in the two-way set associative cache, each block includes 2 cache blocks, right? So there are two sets. What does it mean? So set index field, the number of bits in the set index field is 1. And then we can use this bit as the LSB. The 1 bit LSB in the block address field, right? So cache index is 0, 0, 0, 0, 0. So 8, also the cache index is 0, but what is different? Because in a two-way set associative cache in the target set, the set number 0 includes the 2 cache blocks. So it has the available entry, the available cache block. So memory 0 is not evicted. So in the direct mapped cache, memory 0 was evicted, right? But in a two-way set associative cache, the memory 0 will not be evicted. 0, then because the memory 0 was not evicted, so which means the memory 0 can be found in the cache, that is two-way set associative cache, right? So what's the result? It's hit 6. So the target cache index is 0 because the block address 6 is the 110. So we use the LSB 1 bit as the set index of the cache, right? So the there is no available slot in this for this request. Then so the one of so actually in the target set there were the memory 0 block and then memory 8 block, right? So and then cache the memory 6 was requested. So in this case we need to evict one of these blocks, right? And then so this is called the replacement policy. So what does that mean? Actually, in the direct mapped cache, in the new cache block is requested and missed in the cache, then the original block is evicted from the cache, and then the newly requested block is allocated. But in the set associative cache or in the fully associative cache, so there are multiple valid blocks, right? But if the new block is requested, then we need to evict the one of valid blocks, right? So this is the cache replacement policy, right? So, so in this example, so we assume we use the LRU policy. So we will learn about the LRU policy later. So recently the memory 0 was requested. So memory 0 was accessed. So this is the old access, right? So least recent access, so memory 8. So in this case, we evict the memory block 8 from the cache. So memory 6 is allocated in this cache block. And then the last request is memory block 8. And unfortunately, the memory block 8 was evicted. So in this case, the memory block the result is a miss. So and then the memory block 8 needs to be allocated in the cache. Okay, so in this case, the memory 0 was least recently, so it's a least recently accessed, so memory 0 will be evicted from the cache. Okay, so this example shows the access patterns, so and how the blocks are accessed in the two-way set associative cache. And what is the performance? What is the hit rate of this two-way set associative cache for this example block access sequence? It's 1/5, so it's a 20%. Okay. So how about the fully associative cache? Fully associative cache, the data blocks can be allocated in any available blocks, right? So, and then as I mentioned, so in a fully associative cache, there is no index field. Okay, so block address, then if the newly allocate, then these blocks can be allocated in the available slots. So empty slots, right? So the missed, because the firstly requested is the missed, and then the 8 is also firstly requested, so it's a missed here, and then it's a newly allocated 0. Oh, memory 0 is here, so it's a hit. 6, the memory block 6 is newly requested, so memory 6 is newly allocated. So unlike the two-way set associative cache, then the memory block 6 can be allocated to the empty slot. So any empty slots. So here, and then 8, it's hit. So what is the hit rate? What is the hit rate of this fully associative cache? Is 2/5, it's 40%, right? To understand? So using this example, I showed some performance, the performance differences in the direct method cache, two-way set of associative cache, and fully associative cache. Okay, and then obviously the fully associative cache exhibit the highest performance, highest hit rate, right? So, but then you can think that, oh, in order to increase the performance, then you can use the fully associative cache, right? That is true, right? But what's the problem? What's the problem of fully associative cache? Problem is expensive, right? So cost is high, right? But when you measure, so actually this hit rate of an application is also influenced by the access patterns in the application, in the target application. But it means uh, so we can just run the application on the target CPU, and then we can just measure the hit rate of the target application. Okay, and then usually, so if so in this graph, the set associativity is the x-axis, and then is uh, the y-axis is the hit rate. And then when you measure the hit rate of an application, then it's not linear. And then, so when you measure the hit rate of an application by changing the set associativity of the cache, then actually the hit rate is saturated. So this is the example. So this example shows that so actually the size of data cache is a 64 kilobyte, and then the blocks includes the 16 words, so it means 64 byte, right? And then we just run the spec 2000 benchmarks. And then we use the one-way set associative cache. What does that mean? So it means it's a direct match cache. Then this is the miss rate. So this is the miss rate. Okay. So miss rate was 10% and then 2A. So it's reduced. So miss rate is reduced. Also, what does that mean? So the performance of cache is increased, right? For four-way set associative cache, it's a little bit reduced. The miss rate is a little bit reduced, but if you just compare the gap between the 1A and 2A, and if you compare the the performance gap, the miss rate gap between 2A and 4A set associative cache, you can find that this gap is smaller, right? So when you draw the graph of miss rate, then this graph looks like this, right? So this gap is also reduced for the 8-way set associative cache. So what does it mean? Fully associative can exhibit the highest performance, but it's expensive. And then actually we can just achieve the similar performance. So if we just around set set associative of the cache as 8-way or 16-way, then the performance of this cache can be similar to the fully associative cache. So what does that mean? We don't need to use fully associative cache. The fully associative cache is so expensive. But using the 8-way or 16-way set associative cache, we can achieve the similar performance, right? So that's why we don't need to use the fully associative cache in the commodity CPU. Okay. So if you read the specification documentation of the Intel CPUs or AMD CPUs, then you can find the configurations of the cache hierarchies. Okay, then you can just find that actually the Intel CPUs or the AMD CPUs do not use fully associative cache. Right? So it is because using the 8-way or 16-way set associative caches, we can achieve the similar performance, right? So that's why we do not use the fully associative cache. So this figure shows the example, the cache organization of set associative cache. So as you can see, this cache includes the total 1024 blocks. And then what is the set associative of this cache? How many sets? How many sets in this cache? As you can see, this cache has the set index number 0 to 255, so which means there are 256 sets. So which means a single set includes 4 blocks, right? So what is this? What is this cache? This cache is the 4-way set associate cache. Okay. So so this is the byte offset. What is this? This is the set index field. Then because there are 256 sets in this cache, so how many bits in the set index field? there are 8 bits, right? So using this set index field, we can identify the target sets for this cache, right? So the target set, then we need to compare. So we need to compare the valid bit and then tags in the cache. So you can find the comparators here, and then also we need to check the validity of the cache block. Okay. So as I mentioned, the four-way set associated with cache includes the 4 comparators. Okay. And then one of this tag is matched, and then if the, the cache block is valid, like you can find the valid flag here, then this is hit. Okay. And then the remaining field. So the remaining field is used as the tag field. Okay. So this tag will be stored in the cache. Okay. So this is an example of a four-way set associative cache. Okay. So as I mentioned, if we use the set associative cache or fully associative cache, then we need to consider the replacement policy. Okay. So for the direct method case, we don't need to consider the replacement policy because only one block can be included in a single set, right? But the set associative cache or fully associative cache, and then if there are no valid, if there are no available, so which means if the cache, the target set, or if the cache is full, so which means in the fully associative cache, if the cache is full, then it means that when the new data is missed in the cache, but there is no no empty block in the fully associated cache, right? So set associated cache is the same, okay? If you can just identify the target set, but when the target set, all blocks of this target set are valid, and then if the request is missed in the cache, then we need to evict one of the valid blocks. That's why we require the replacement policy. Okay, and then we frequently use the least recently used policy. So it's called the LRU. So it's a LRU policy. So it means the least recently used cache replacement policy. What does that mean? So as I mentioned, so actually I also explained about the LRU policy here, right? So it means if a cache block is least recently used, then this block will be evicted from the cache. Okay, so this replacement policy is the least recently used. So we can also apply the random replacement policy, which means that among the valid blocks, the the block which will be evicted can be selected randomly. Okay, so it is because the LRU. So LRU is just simple for the two-way set associative cache, but it's manageable for four-way set associative cache. But it's so hard if the set associativity of cache is increased. Okay, so if we use the 8-way or 16-way set associative cache, then LRU implementation is so complex. So actually the commodity CPU vendors such as Intel or AMD actually use the simplified version. So simplified version of LRU. Okay. So sometimes the CPU vendors such as ARM actually apply random policy, random replacement policy. So which means, so we can just randomly select which the cache blocks which will be replaced. Okay. So sometimes so for the set associative or the fully associative cache, then we need to consider the replacement policy. And then this replacement policy also influences the performance of a cache. So which means the hit rate of the cache can be also influenced by replacement policy. Okay. And then also let's see the performance impact of the multi-level cache. Okay. So if you see the memory hierarchy, so the memory hierarchy looks like this. So this is the register file, and what is this? This is cache. But in the cache, you can find the level 1, level 2, level 3 caches. So what does that mean? Actually, the way the commodity CPUs use multi-level cache, right? So multi-level cache means that, so this is the CPU, and then CPU firstly access level 1 cache, and then if the level 1 is missed, then the CPU accesses level 2 cache, and the missed CPUs accesses level 3 cache, and the missed is a memory. Okay, and then usually the cache is including the CPU package. So actually we can use the multi-level cache. So what is the benefit? What is the benefit of multi-level cache? So then what is the characteristics of this high-level cache or low-level cache? So we learned about the characteristics. The characteristics of the memory hierarchy. The memory hierarchy level is high, so which means this memory is small but fast. If the memory hierarchy level is low, this memory size is large, but it's slow. The same characteristics can be applied to the multi-level caches. So level 1 cache is faster, but size small. Level 3 cache is slower, but size is large. So if you read the CPU specification, then you can find that the level 1 is the size of a level 1 cache is small. The size of a level 3 cache is large. So why? Because as the cache size increases, the access time, so which means the performance of a cache is decreased. Access time is increased. Okay. So this is the property of the memory. Okay, the memory component. Okay. So we can organize the multi-level cache hierarchy, CPU. Okay, like level 1, level 2, and level 3. Then what's the benefit? So this is the example of a multi-level cache example. The base CPI, the ideal CPI is 1, and the clock frequency is 4 GHz. A miss rate per instruction is 2%. The main memory access time is 100 nanoseconds. So if it just CPU just includes the level 1 cache, so it looks like this: CPU, and then level 1 cache, and memory. So then what is the miss penalty? So when the cache miss is encountered, then the CPU needs to access main memory And then main memory latency is 100 nanosecond. And then the CPU clock frequency is 4 gigahertz. So the clock period is 0.25 nanosecond. It's the 400 cycles. It's the miss penalty. So the effective CPI is 1 plus the miss rate is 2%, 2%. So 2% multiplied by 400 miss penalty. So effective CPI is 9. Okay, but let us assume that the CPU includes the level 2 cache. So it looks like this is the it's a CPU, and then level 1 cache, and then there is also larger level 2 cache. So if we just see the access time is 5 nanoseconds. What does that mean? It's slower. But if we just see the miss rate, this miss rate is reduced, right? The global miss rate to main memory is 0.5%. Okay, so this is the miss rate in the L2 cache. Okay, so what is the primary miss with L2 hit? So what is the miss? What is the miss in the L2? So the first, which in this case, the CPU firstly access L1, right? Then if the cache miss is encountered, then the CPU will access L2, right? So when the miss is encountered in the L1, then what is the miss penalty to L2, right? So miss penalty. So if the data is hit in this L2, so request is hit in this L2, then this miss penalty is 20 cycles, right? Because the access latency to L2 is 5 nanosecond, and then the clock frequency is 4 gigahertz. The clock period is 0.25 nanosecond, so it's a miss penalty. So the hit, this is the L2 hit case, right? So we can also just consider the L2 miss case, okay? So in the L2 miss case, then the extra penalty is 400 cycles, right? So what is the effective CPI? CPI, this is CPI, and then this is the miss penalty, but this miss penalty is the L1 miss and L2 hit, right? What is this miss penalty? This miss penalty is L2 miss penalty, right? So this is the miss penalty, and then this is L1 miss and then L2 hit, okay? So this is a miss rate in L1. Then this is a miss rate in L2, right? So this is the CPI. Then how much performance is improved? So we can just compare the CPI in this case. So the multi-level cache. So using the multi-level cache, then we can also improve the performance, right? Then you may think that, oh, instead of Aeron cache, then we can increase the size of the Aeron cache. Then what's the problem? The problem is access latency. So what is the benefit of L2? So L2 cache size is larger than the Aeron cache size. The, what is the disadvantage? What is the overhead? So disadvantage of large L2 caches, the access latency is also increased, right? So which means the heat time is increased, right? So if we use the larger L1 cache, what's the problem? Heat time. Heat time will be increased. So what does that mean? Even though the cache is hit in the request is hit in the L1 cache, then if the heat time is high, then the pipeline needs to be stalled, even though the request is hit in the cache, right? So performance can be decreased. So that's why we just use the small cache for the level as the level on cache, right? So this is the design policy of the cache hierarchy. For the primary cache, it means the add-on cache, we just minimize the hit time, right? So in order to minimize the hit time, so which means we need to reduce the cache access latency. So what does that mean? We need to reduce the size of the cache, right? So we need to reduce the hit time. For the L2 cache, so when we design the L2 cache, then we can make the miss rate lower using the L2 cache, right? So by doing this, so we can increase the hit rate. So if the cache size is increased, then the cache can include the more cache blocks, right? The larger data. So what does that mean? So we can reduce the miss rate, right? So using the L2 cache, so we can reduce the miss rate, right? So this is some configuration, okay? Some design policy of the multi-level cache. Okay, so I will skip here because we did not learn about the out of order CPUs, right? Okay. Then let's learn about some impacts, the impact from the workload. Okay, so what does that mean? So I mentioned that the actually the cache hit rates are influenced by workload. So it depends on access patterns in applications. So what does that mean? Which means if the so if we just learn different applications, then we can observe different cache hit rates or cache miss rates. We obviously, right? Because the access patterns varies by access patterns vary, so access patterns are different by application. Okay, so let's see the impact from the application. Okay, and then let's see how we can improve the performance of an application by considering cache size. Okay, so let's see the example. So what is this? This code is the general matrix multiplication code, right? So as you can see, the general multiplication like C equal A multiplied by B. So A is also a matrix, and then B is a matrix, and then we can just get the result matrix C by multiplying A and B, right? Then, so this is the code, okay? So this is the general matrix multiplication code. So as you can see, we can just access the elements in matrix A and the elements in matrix B, and then by performing the dot product between the row of matrix A and a column of matrix B, then we can get the result value for the target element, right? So in a matrix multiplication, in order to calculate this element, will require one row of matrix A and then this row of this column of matrix B. So this row is we just perform that product between this row of matrix A and then this column of matrix B, right? Then we need to and then we can compute the next element. Then what is required? For matrix A, the same row will be requested. How about the matrix B? The next column will be requested. Then next element. So when you compute the elements in a row in matrix C, then we can just use the entire row of matrix A. But for matrix B, we require entire elements, all elements in matrix B, because the column is used. Then what's the problem? Problem is, if the matrix size is large, a cache cannot store entire elements in the large matrix. What's that mean? What does that mean? Sorry. So if the matrix is size is large, the matrix A is okay because the same row will be repeatedly used. But the matrix B, column is used. This column is used. And then if the matrix size is large, when this column is requested, then if the cache size is small, then the old data can be evicted from the cache, right? And then if this column is requested, then also this column, the column 1, can be evicted because the cache size is small. So what does that mean? For the next row, we also request this column for computing this element, but this column is already evicted from the cache. So we can observe locality in the matrix multiplication. What's the problem? The locality is not utilized in the cache because the cache size is small. Then how can you improve the performance? We can partition the matrices. So we can also apply the enhanced algorithm so that utilizes partitioned submatrices. Okay, so this is the algorithm. Okay, this is the matrix multiplication using partitioning. So what is the benefit of partitioning? So if we just use the smaller submatrices, then we can reduce the size of matrix multiplication, the size of matrices. So this is the example. If we just use the smaller matrix for this matrix multiplication, then we can also reduce the size of matrix B, the submatrices in the matrix B. Then all elements of this matrix can be included in the cache. Then we can utilize the data locality in the matrix multiplication. Do you understand? So this is the unoptimized version. So it's the normal matrix multiplication, and then this is the blocked matrix multiplication. So it means the large matrix is partitioned into the smaller submatrices, and then we perform the matrix multiplication between the smaller submatrices. And then you can find the size of uh, the, the matrices, right? And then the y-axis represent the performance. It's a G flops. It means the giga floating operations per second. So it can be also used as the performance metric. Okay, for the unoptimized version, you can find that the performance is reduced if the size of a matrix is increased. Why? Because the large matrices cannot utilize the cache. So which means we can, even though we can observe locality, but because the cache size is small, this locality is not utilized in the cache. Okay, which means the hit rate is low. Because the hit rate is low, the performance is decreased dramatically. So if we just compare the performance between 32 by 32 matrix and then 260 by 260 matrix, then you can find that the performance is lower than the half of the 32 by 32. But if we use the partitioned matrix multiplication, so it's called the blocked matrix multiplication, then you can find, but it's marginally. The performance is marginally reduced, decreased. Okay, so what does it mean? We can develop algorithm. we can develop software algorithm that can utilize the cache. They can increase the performance of cache. Okay, so this is the example. We can apply the blocked matrix multiplication to improve the performance, and then to utilize the cache more efficiently. Okay. Okay, so I will summarize the cache, so memory hierarchy. So you need to understand the benefit of a memory hierarchy, right? So, and then also you need to understand why CPUs use memory hierarchy. Okay. And then we also learned about the direct mapped cache, and then NA set associative cache, and then fully associative cache, right? And then so when we organize the cache, then we need to consider some performance and the cost of the cache. So this is you can just understand the set associative cache and the direct mapped cache and the fully associative cache like this, right? And then we also learned about the replacement policy. We learned about the write policy, it's a write through or write back policy, right? And then I will briefly explain about the source of misses. So what does that mean? We can analyze why cache misses occur. Cache misses are encountered in the cache, but we can just analyze why these cash misses are encountered. So what are the reasons of these cash misses? So sources of misses. So it just categorizes the reasons of cash misses. So actually there are three reasons here. So it's called the 3C of caches. Okay. So it just analyze the reasons of cache misses. The first reason is the compulsory, first category. The first category is the compulsory misses. So it's called the cold misses. So it's a C or C. Okay. So what does it mean? If a data is firstly requested, then the cache cannot include this data, right? So this type of misses are called cold misses or compulsory misses, right? We cannot, okay? So if the data is firstly requested, then it's a cold misses. Then how can you reduce the cold miss rate? So if we increase the cache block size, then we can reduce the cold miss rate. So think about this. If the cache block size is large, and then when this data is missed, requested, then the entire block, so this amount of data is allocated in the cache. Then if the block size is large, then the next request can be hit in the cache, right? So you may think that, oh, we cannot avoid the cold misses, but we can reduce the cold miss rate because if we increase the cache block size. The second source of misses is capacity misses. What does that mean? The cache size is small, right? Actually the cache size is limited. So and then because of this limited size of cache, then the cache miss can be caused. Okay, and then this type of misses are called capacity misses. So it means it's the misses caused by cache capacity. Conflict miss, so also called the collision misses. So we already know that if we use the fully associative cache, then the performance, it means the cache hit rate is can be higher compared to the set associative cache or direct mapped cache, right? So what does it mean? Because of set associativity, the cache misses can be increased. So if we just recognize the cache misses are increased compared to the fully associative cache, then this type of misses are called conflict misses. Okay, so these are called the 3Cs of cache. Okay, it just explains the source of cache misses. So if we increase the cache size, then we can reduce the capacity misses. Okay, but may increase the access time, right? Because hit time can be increased. So if we increase the associativity, then we can reduce the complex misses, but may increase the access time also. The cost can be increased. If we increase the block size, we can decrease the compulsory misses, right? So miss penalty can be increased, right? And then also we can observe the cache pollution. Okay. Okay, so this is the summary of cache. Okay. Uh, And then I hope students can understand the organization of the cash and then also the cost and performance of cash. Okay. Okay. Thank you for your attention, and then we will learn about the virtual memory next class in the next class. Okay. Okay. Thank you. 감사합니다.